So now what I want to practice is I want to practice being given one thing like an H plus ion concentration and turning it into something else like a hydroxide ion concentration. Eventually being given any one thing, H plus concentration, OH minus ion concentration, pH or pOH, and turning it into the other three. So for example, this top one, what is the hydronium ion concentration if the hydroxide ion concentration is 2.6 times 10 to the negative third? Well, you can convert between hydronium and hydroxide concentrations just using the mass action expression and the ion product constant for the auto ionization of water. So what is the hydronium ion concentration? We'd be solving for that. If the hydroxide is this, and that's the constant, go ahead and solve for that, folks. Lily. You said H plus times OH minus has got to equal 1 times 10 to the negative 14. So H plus hydroxide, 2.6 times 10 to the negative third, and then 1 times 10 to the negative 14th. Divide both sides by 2.6 times 10 to the negative third. Looking like two sig figs here, folks. Don't let the 1 times 10 to the negative 14th ever limit your sig figs. That's a constant. That's considered to be a pure value. So don't ever let that limit your sig fig. It's just like the definition for the, for the auto ionization of water. So the H plus ion concentration would be 3.8 times 10 to the negative 12. Let's try one more of those. Try this next one here. What's the hydroxide ion concentration if the hydronium is 5.16 times 10 to the negative third? Right. You should get, when you do that, 3 sig figs. I got 1.94 times 10 to the negative 12 molar. So if you have a solution that contains 5.16 times 10 to the negative third molar hydronium, then it must have 1.94 times 10 to the negative 12 molar hydroxide as well. Any solution that has hydronium has to have hydroxide, because when those two multiply by each other, when you multiply those two by each other, it's got to be 1 times 10 to the negative 14. Can't have hydronium without hydroxide. Can't have hydroxide without hydronium. But if one goes up, the other goes down. All right. So now I want to talk about getting the pH of strong acids and strong bases. And you guys are going to love this because strong acids are so easy, and strong bases are so easy to get the pH of because they fully dissociate. And since they fully dissociate, you know the H plus or OH minus ion concentrations. For example, if I have a solution of 0.0010 molar HCl, since that is a strong acid and it fully dissociates into H plus and Cl minus, here's the beautiful thing. Okay, if it's 0.0010 molar HCl, that has all dissociated. And that means it's 0.010 molar H plus and 0.001 molar chloride, but I don't care about the chloride. So that is my H plus ion concentration. So strong acids and strong bases, since they fully dissociate, they let you get the H plus ion concentration if it's a strong acid very quickly, and they'll let you get the hydroxide ion concentration if it's a strong base very quickly. So for example, in this solution, we could get the pH rather quickly because pH is the negative log of the H plus. Since that's a strong acid and it has fully dissociated, we can just plug that in for the H plus ion concentration. So the negative log of 0.0010, that's got 2 sig figs. We're going to go 3 places past the decimal. That would be a solution with a pH of 3.00. So go ahead and try this top one. What's the, let me ask you this first before we get all tricky. Let me ask you first, what's the pH of a 1.50 times 10 to the negative fourth molar HCl solution? And then I'm going to ask you what the pOH is. So give me the pH first. That's not being a trickster. And then once you get the pH, can you give me the pOH? So HCl fully dissociates. Since it fully dissociates, that is the H plus ion concentration. That's it. So go ahead, calculate the pH of that solution. So the pH is the negative log of the hydronium ion concentration. Since this is a strong acid and it fully dissociates, that is the hydronium ion concentration. Now, when we get to the weak acids, you are not going to be able to do that. So that's going to be 1.50 times 10 to the negative fourth. And that's going to be 3 sig figs. So we're going 3 places past the decimal. 3.823 would be my pH. Now, oh, no, 3.824 with rounding. Let's get that right, 3.824. Now, if I want the pOH, remember, pH plus pOH has to equal 14. So 14 minus that will get me the pOH of the solution. So 14 minus 3 that's going to be 10.176 as my pOH. That's my pOH. Try again. How about this guy? The strongest strong acid. Again, there is another classification of acids called a superacid, but of the 6 strong acids, nitric acid is the craziest because you can make it the most saturated in water. I'd like you to tell me what's the pH of a saturated 15.8 molar nitric acid solution. Go ahead. So we're going to take the negative log of 15.8. So the negative log of 15, negative log of 15.8. That's going to be a negative, and we get to go 3 places past the decimal, so negative 1.199. That would be my pH, negative 1.199. So rather acidic, right? You get a pH of negative 1.199. That's an acidic solution, right? That's really the most acidic those 6 strong acids can get. Okay, so now I want to talk about the strong bases. What does it mean to be a strong base? Well, strong bases fully dissociate. They're the alkaline earth metals paired with hydroxide. So if you put sodium hydroxide in water, sodium hydroxide is going to fully dissociate because it's strong. That's what it means to be strong. And it's going to break up into sodium and hydroxide. So here's the cool thing. If this is the sodium hydroxide concentration and it fully dissociates, that's also the sodium ion concentration, who cares about that, and the hydroxide ion concentration. So if you are given the concentration of a strong base, that is your hydroxide ion concentration, you can go right into a pOH. So pOH is the negative log of the hydroxide ion concentration. Go ahead, get me the pOH of this solution, and then give me the pH. Go ahead. I'll do it too. That's going to be a pOH of 3.301, and then 14 minus that. Again, 3 sig figs, so I went 3 places past the decimal. 14 minus that, that's going to be a 10.699 pH. So again, not surprising. Most people are a little better with the pH scale than the pOH scale. You got a pH above 7, you're basic. That's a basic solution. I will caution you with alkaline earth metal hydroxides. You need to be careful. Barium hydroxide is an alkaline earth metal hydroxide. So what does that mean? Well, let's write its dissociation out. So it's an alkaline earth metal hydroxide. It's going to fully dissociate. And it's going to break up into a barium cation and 2 hydroxides. That's going to be really important. Because if this is the concentration of barium hydroxide, then the hydroxide ion concentration is going to be twice that. Think about it. If I have 500 bicycles, I take them apart, that's 1,000 wheels, right? I need to double that to get the hydroxide, right? So 5 times 10 to the negative 4 times 2, that's going to be 1 times 10 negative third, or 0.00100 molar for the hydroxide ion concentration. Now that I have the hydroxide, so again, be careful. If you have an alkaline earth metal hydroxide, to get the hydroxide concentration, you got to double the alkaline earth metal hydroxide concentration. So now go ahead and give me a pOH and then give me a pH. Go ahead. So that's going to be negative log of that. That's going to be a pOH of 3.000. And then 14 minus that, that's going to be a pH of 11.000. So hopefully you see how the sig figs work on that with the logarithms. And I will grade certain questions on the test based on getting those sig figs right. So what have we been able to do? Well, if I give you a concentration, whether it be H plus or OH minus ion, or I give you the concentration of a strong acid or a strong base, you can get everything else. But what if I give you a pH or a pOH and I want you to work backwards and get me a concentration? How does that work? Here's a really important formula. So you could title this in your notes, Undoing pH or pOH. We're actually going to derive the formula because I feel like if we do that, maybe it'll stick a little better. So here's what I want to do. Right now, the pH formula is set up to solve for pH. But I want to solve for H plus. So how could I take a pH and turn it into an H plus? Well, first thing, let's divide by -1. And we get negative pH equals log of the hydronium ion concentration. And then we have to undo log. So 10 to the on both sides. And what we end up with is the hydronium ion concentration of a solution is equal to 10 to the negative pH. Let's test it out. What if I told you that a solution had a pH of 1.15? What would the hydronium ion concentration be? Well, the hydronium ion concentration is 10 to the negative pH. So 10 to the negative 1.15. That would be a hydronium ion concentration. Now, we have to try to apply the sig fig rule backwards. Okay, first thing, if you put that in your calculator, please put that in your calculator. If you put that in your calculator, you're going to get 0.0707945. So I'm just going to write that down here. We're going to worry about sig figs here in a second. I mean, that's a concentration, so molar, if you want to throw a unit on it. Now, you have to apply that sig fig rule in reverse. So the number of place values past the pH, that's how many sig figs this has to happen, right? But we're going backwards. So that's 2 places past the decimal. That's 2 sig figs. This would be 0.071 molar. Now that 0 is a leading 0. It doesn't count as a sig fig. So you can see how we work backwards there. Now the same thing is going to be true for pOH, okay? And undoing pOH, we could again derive that formula. The pOH of a solution is the negative log of hydroxide. If we want to get this in terms of hydroxide, we divide by -1. So negative pOH equals the log of hydroxide. 10 to the on both sides. The hydroxide ion concentration equals 10 to the negative pOH. And that's how we get our hydroxide, 10 to the negative pOH. So once again, I'll give you one more. Why not? If the pOH of a solution is 3.15, what is the hydroxide? I tell you what, 3.15 is 0. Let's throw a 0 on there, right? Just to give you a tricky one with the sig figage. What must the hydroxide ion concentration be? Go ahead. All right. So 10 to the negative pOH. 3 places past the decimal, so I want 3 sig figs. That's going to be 7.08 times 10 to the negative 4th molar, or 0.000708, right? So hopefully you guys feel good about that. You should now, with these formulas, should now be able to take any one of the 4 things. If I give you an H plus concentration, you should be able to give me a hydroxide, a pH, and a pOH. If I give you a pOH, you should be able to give me the other three. You should be able to give me a pH, an H plus, or an OH minus on concentration. You should be able to do all three, right? Given one value, you should be able to get the remaining three. I would like you to try number one here, a solution that contains 8.75 grams of sodium hydroxide in 785 milliliters of solution. I would like the H plus, the OH minus, the pH, and the pOH of that. So the first thing you have to do is get that hydroxide ion concentration. So you have to turn that into moles. And then you got to divide that by the volume in liters. So let's see at first. First thing, can you get me a molarity of sodium hydroxide? Let's start there. All right, so the first thing we need to do is divide that by the molar mass of sodium hydroxide. So 22.99 plus 16 plus 1.01. It's got a perfect molar mass of 40. So 8.75 divided by 40, that's 0.219 molar sodium hydroxide. Since that's an alkali metal hydroxide, it fully dissociates, okay? Oh, I'm so sorry. Hang on, that's not molar. Well, I'm getting ahead of myself. That's just moles. Oh my goodness. That's just moles of sodium hydroxide. Now we need to divide it by the volume in liters. Remember, molarity is moles per volume in liters. So we need to divide that by 0.785 liters. We're going to divide this by 0.785 liters to get a molarity. 0.219 divided by 0.785. That molarity is 0.279 molar sodium hydroxide. And 3 sig figs divided by 3 sig figs, 3 sig figs. So you actually have one of the three things, one of the four things. Because sodium hydroxide is a strong base and it fully dissociates, that is the hydroxide ion concentration. So now, can you turn that into a hydronium? Can you turn that into a pH? And can you turn that into a pOH? Take a second, now that we got the concentration of sodium hydroxide, which is the hydroxide, can you turn it into the other three? There are multiple ways to do this and get this right. Try to keep track of sig figs. Do your best to get the sig figs right. Go ahead. Can you turn it into the other three? You should be able to take any one of these four things, turn it into the other three. Give it a shot. Some options. I'm going to show you how I would do it. First thing I would do with the pOH or the hydroxide ion concentration is I'd actually get a pOH. So if we do pOH is the negative log of hydroxide. If we plug that on in there, negative log of 0.279. We got 3 sig figs. We're going 3 place values past that. So negative log of 0.279. That's going to be a pOH of 0.554. So that's a pOH 0.554. Then I would get a pH. So 14 minus that, if that goes out to the thousands place, we won't continue to go out to the thousands place. That's a pH of 13.446. Then I can undo that pH, right? The hydronium ion concentration is equal to 10 to the negative pH. So 10 to the negative 13.446. That's going to be a hydronium ion concentration of 3.58 times 10 to the negative 14. So 3.58 times 10 to the negative 14th molar. Those are your four values, right? Now, this is not the only way that you could have solved this problem. You could have, once you had hydroxide, you could have got H plus, because hydroxide times H plus has to be 1 times 10 to the negative 14th. So 1 times 10 to the negative 14th divided by 0.279 should have got you that. And then once you had that, you could have got the pH and the pOH, right? I mean, you could do it. So there's multiple ways to do these problems. Number two, looks hard at first, okay? But it's not that bad. Here's why it's not that bad. Because this is a mixture of two strong acids. So it wants the H plus ion concentration, hydroxide, pH, and pOH. Because this is a strong acid and this is a strong acid, they're both going to fully dissociate. Now, you may ask, why on earth would I want to mix two strong acids? Well, they can have interesting properties. For example, the most famous mixture of strong acids is a mixture of hydrochloric and nitric acid. That's called aqua regia. That's so potent and strong it can dissolve gold, which is very hard to do. Okay, the alchemists actually discovered that. That's some crazy stuff. But anyway, here's what happens. This fully dissociates. So that's the H plus ion concentration from the HCl. This fully dissociates. So that's the H plus ion concentration from the HClO4. And what I can do is I can just add those together where the H plus ion concentration of the mixture is going to be the sum of those two. So 0.0555 plus 0.0785, that's an H plus ion concentration of 0.1340. So people, when they get, and I went out 10,000th place plus 10,000th place, we got to go to 10,000th place, we'll throw a trailing zero on there. People freak out when they see those kinds of problems. Then we could get the hydroxide ion concentration. Let's do it the opposite way. If we take 1 times 10 to the negative 14th divided by that, so 1 times 10 to the negative 14th divided by 0.1340, that would be a hydroxide concentration of 7.463 times 10 to the negative 14th molar. There we go. And now I can get the pH and pOH of these, right? So if I take the negative log of the H plus, you get, that's 4 sig figs. We got to go 4 places past. We get 0.8729. And then the pOH, take the negative log of the hydroxide, negative log of 7.463 times 10 to the negative 14th. That would be a pOH of, sorry, this stupid zoom bar popped up here, 13.1271 would be my pOH.